Welcome to Math Vision tutorial. My name is Moses. In the last class, we talked about electric force. Today, we shall continue with electric field. What is an electric field? An electric field E is the region or space where electric force can be felt or experienced by a charged body. Yes, an electric field is the region or the space where electric force can be experienced by a charged body. Let's consider a football field. On a football field, the playing of football takes place on a football field. So what happens in an electric field as well? In an electric field, we have the interaction of forces in such a way that when a test charge is thrown into that region, the test charge will experience a kind of force. So now that we understand that an electric field is the region or space where electric forces can be experienced or felt by a charged body. How does electric field come into existence? How do we find electric field? Where do we find electric field? Now, remember that we have two types of charges, which are the positive charge and the negative charge. Charges create electric field. Let's consider myself to be a charge. In the region or the spaces around me, I have what we call electric field. In such a way that if another person comes into my region, remember that the person must also be a charged particle, a charged body. If another person comes into my region, the person will experience a force due to the electric field that I have created because the person is coming into my region. Remember that we said an electric field is the region or space where electric force can be experienced by a charged body. So, as I have created electric field around myself. If another charged body comes into my region, the charged body will experience a kind of force. So now, the magnitude of an electric field E at some point in space on a test charge Q is given by E equals to F over Q. Remember that this E is our electric field and the F is the force, while Q is the charge on which the force is acting. Q is the test charge on which the force is acting. So now, notice that an electric field E is a vector quantity because it has magnitude and direction. From equation 1, it can be seen that the unit of an electric field is Newton per coulomb. Yes, because the unit of force is Newton and the unit for a test charge is coulomb. So this is Newton per coulomb and that is the unit of an electric field. The unit of an electric field is Newton per coulomb. So now, notice the following. Electric fields point away from positive charges to the point of creation. Remember that I said that charges create electric field. Let's consider this first figure here. This is a positive charge. Around this positive charge, every point in space around it, this positive charge has created what we call electric field. So at every point in space around this positive charge, there's presence of what we call electric field. Now, what is the direction of the electric field? Remember we said that an electric field is a vector quantity. It has to point in some direction. An electric field will point away from positive charges to the point of creation. If I'm considering this point, the direction of the electric field will be from this positive charge to the point of creation. At every point in space, the direction of the electric field will point away from the positive charge. And now, electric field points towards negative charges from the point of creation. Now, how does electric field point? In what direction do they point? Due to a negative charge. Due to a negative charge, remember that this negative charge also creates electric fields around itself. So the direction of the electric field will point towards the negative charge from the point of creation. Now, when a positive test charge Q naught is placed in an electric field, what happens to the charge? We understand what an electric field is. An electric field is the region or space where electric force can be felt or experienced by a charged body. Quite simple and easy. So we know where to find electric field and what causes electric field. We know that charges causes electric field. Charges create electric fields around themselves. Static charges, yes. Static charges create electric fields around themselves. So now, we also know that if a positive charge creates an electric field, the electric field will point away from the positive charge to a point of creation. And a negative charge, if a negative charge creates an electric field, the electric field will point, the direction of the electric field will point inwards to the negative charge. So now, what happens to a test charge, to a positive test charge, if it is thrown into an electric field? In what direction will the positive charge move? The positive charge will tend to move in the same direction as the direction of the field. When you throw a positive charge into an electric field, remember that it will feel a force. But in what direction will the electric field, will the charge move? The charge will move in the same direction as that of the electric field. But when a negative charge is thrown, when a negative charge is thrown into an electric field, the electric field, the negative charge will tend to move in the direction opposite to the electric field. So now that we understand the basics concept of an electric field, it's time for us to know the magnitude of an electric field due to a point charge at a distance from the charge. So now, we know that the magnitude of an electric field is given by force per charge. The magnitude of an electric field is given by the force divided by the magnitude of the charge. And by Coulomb's law, the force on a charge, as given to us by Coulomb's law is K multiplied by the magnitude of Q1 multiplied by the magnitude of Q2 over R squared. And by putting the equation 3 into 1, that is, by substituting this value for F in 1, we have that the electric field E is equal to K multiplied by the magnitude of Q1 multiplied by the magnitude of Q2 over R squared divided by the magnitude of Q. Don't forget that the magnitude of the electric field is force divided by the magnitude of Q. Force divided by the magnitude of Q. And the force here is this. So we have the electric field to be force divided by the magnitude of Q. Then changing this division to multiplication, we have that K multiplied by the magnitude of Q1 multiplied by the magnitude of Q2 over R squared multiplied by 1 over the magnitude of Q. And by multiplying these two together, we have that the electric field now is K multiplied by the magnitude of Q1 multiplied by the magnitude of Q2 over R squared multiplied by the magnitude of Q. So, this magnitude of Q in the denominator, we cancel one of the magnitude in the numerator. So, this magnitude of Q, we cancel one of these, and finally we have that the magnitude of the electric field now is K multiplied by the magnitude of Q over R squared. So now, this is the magnitude of an electric field produced by this charge Q. And the magnitude of this electric field is the same as the magnitude of the electric field here. Depends on the question given to you. Based on the question given to you, in the question given to you, if you are asked to calculate the magnitude of an electric force, given the distance at which you want to calculate the magnitude of the electric force, and given the charge, you are going to use this. And if you are asked to find the magnitude of an electric field in another question, given the force and given the charge, you are going to use this. So now, we have some questions to look at under electric field. The first question says, an object having a net charge of 24 microcoulombs is placed in a uniform electric field of 610 Newton per coulomb. That is the magnitude of the electric field. Directed vertically, that is, the direction of the electric field is vertical. Full stop. What is the mass of this object if it floats in the field? What is the mass of the object if it flows in the field? Now let's take a picture of what the question is all about. This is the charged body. The charged body that is having a charge of 24 microcoulomb. This is the charge body. Don't forget that it is positive, so it means the charge body is a positive charge. So now this is the charge, and the direction of the electric field at which the body is thrown is vertical. So that means since this body is a positive charge, that means this body will tend to move in the same direction as the what? As the electric field. So the force on this charge now, the force on this charge due to this electric field will tend to move this charge in the same direction as the electric field. And the force on the charge is given as electric field multiplied by the magnitude of Q. Don't forget that the magnitude of electric field E is F over magnitude of Q. And this is the force on the charge. Cross multiplying this, we have that the force on the charge is E multiplied by the magnitude of Q. And that is how we have the magnitude of the electric force to be equal to E multiplied by the magnitude of Q. So now, the force on this charge due to this electric field will move this charge in the same direction as the field. And the magnitude of the force on the charge is simply the electric field multiplied by the magnitude of Q. But don't forget that it is not only the force due to the electric field that is acting on this charge. There's another force acting on the charge, and the force acting on the charge is the gravitational force. The gravitational force will be pulling down this charge. But from the question, we have to find the resultant force. Yes, we have to find the resultant force to know the direction in which this charge is moving towards. Now, from the question, we are told that the charge did not move in any direction. And that means that the charge is static. It's static because we are told from the question that the charge floats, the body floats. So we want to find the mass of the body if the body floats in the field. That is, if the body did not move in the direction of the field. And why will the body remain static? The body will remain static if the magnitude of the gravitational force is equal to the magnitude of the electric force. Because if they are both equal, the force pulling it up and the force drawing it down, if they are equal in magnitude, that means that the charge will remain at the same position. That is when the charge will remain static. So now, for this charge to float, that means that the magnitude of the electric force is equal to the magnitude of the gravitational force. So we have that EQ is equal to mg. And by making m the subject of formula, because we are looking for the value for n, then m will be EQ divided by the acceleration due to gravity, which is g. From our question, we have that the magnitude of the electric field is 610 Newton per coulomb multiplied by the magnitude of the charge. The magnitude of the charge is 24 microcoulomb, which is 24 times 10 raised to the power minus 6 coulombs, over the magnitude of the acceleration due to gravity, which is a constant, and that is 9.8 meters per second square. Evaluating this on your K-show calculator, we have that the mass is 1.5 times 10 raised to the power minus 3 kilogram. And that is all for the first question. Now we have the second question. The second question says, an electron is released from rest in a uniform electric field of magnitude 2.00 times 10 raised to the power 4 Newton per coulomb. Calculate the acceleration of the electron. Yes, calculate the acceleration of the electron. And here we are asked to ignore gravitation. Yes. So now, we have that the force on a charge in an electric field is given as F equals to E multiplied by the magnitude of the charge. So the force on the charge in the electric field here is given as F equals to magnitude of electric field multiplied by magnitude of the charge. And by so doing, from the question we have that the electric field is 2.00 times 10 raised to the power 4 Newton per coulomb, and multiplied by the magnitude of the electron. The magnitude of an electron is a constant, which you have to know often. The magnitude of an electron is 1.602 times 10 raised to the power minus 19 coulombs. So now, by multiplying these two together, we have that the force on the electron in the field is 3.20 times 10 to the power 15 Newton. That is the force on the electron in the field. And from the question, we are told to ignore the gravitation, because if we are not told to ignore the gravitation, we know that it is not only the electric force that is acting on the electron. There must be a gravitational force also acting on the electron. So we have to find the gravitational force as well and resolute the gravitational force and the electric force together to get the resultant force. But here we are told to ignore the gravitational force. That is, we have to concentrate only on the electric force. So now it means that the force acting on the electron only is the electric force. And force is given as 3.20 times 10 to the power minus 15 Newton. And by Newton's second law of motion, we have that F is equal to ma. Yes, the force on a body is equal to ma. And now, by making A the subject of formula, we have that A is equal to F over m. And the force acting on the body, as we have calculated, it is 3.20 times 10 raised to the power minus 15 Newton. It is 3.20 times 10 raised to the power minus 15 Newton divided by the mass of an electron. The mass of an electron is a constant as well, and that is 9.11 times 10 raised to the power minus 31 kilogram. It is a constant. 9.11 times 10 raised to the power minus 31 kilogram. And by evaluating this on the ratio calculator, we have that the acceleration of the electron is 3.51 times 10 raised to the power 15 meter per second. So now I have some practice questions for you. And the practice questions are just two. The first question here is an electron initially at rest is placed in an electric field of 5 times 10 raised to the power 5 Newton per coulomb, directed to the west. Now, what is the acceleration of the electron due to the electric field? That is the question for number one. Remember that we've done something like this in the previous examples. You can check on the example to know how to solve this. And for the second question, we have that we should calculate the electric field intensity produced by a positive charge of magnitude 20 microcoulomb. Here we are asked to find the electric field intensity. And the electric field intensity is the same as the magnitude of the electric field. And we know how to find the magnitude of the electric field. Please endeavor to solve these two practice questions. And if you have any problem or any question concerning today's topic, you can please drop in the comment box below. And please subscribe to my YouTube channel, and don't forget to click on the notification bell to get notified whenever I drop a new video. And please don't forget to like the video as well. See you in my next class.